Good afternoon. It's Riccardo on Wednesday about 5 o'clock. I'm trying to do a video in advance to see if I can get all the kinks out in advance of teaching it tomorrow. So let's see how this goes. We're taking a look at temperature and rate of a chemical reaction. This is lesson 6.4. All right. So this is sight unseen. Uh, this uh, this activity, so to speak. Yeah, boom, boom. All right. So I usually start off with 898, so I'm going to go with 898. All right. So previous lesson, you saw that two clear colorless liquids could be combined to produce a solid precipitate. The formation of a precipitate is evidence that a chemical reaction occurred. In this lesson, you'll investigate whether heating the reactants has an effect on how fast the reaction happens or the rate of a reaction. You'll look at models of the atoms and molecules in the reaction to get a better idea about why heating reactants has an effect on the reaction. Okay, so that's what we're doing today. All right, so how a light stick works. Let's take a look.
Here is a light stick or a glow stick. Let's look at what's inside and consider how it creates light. The light stick is made of a thin, inner, breakable glass tube inside a thicker, flexible plastic tube. The inner glass tube contains a solution of one type of chemical, and the outer plastic tube contains a solution of a different chemical. When the light stick is bent, the inner glass tube breaks, and the solutions in the inner and outer tubes mix and react. The light given off is evidence that a chemical reaction is happening. A bright glow stick means that the reaction is happening quickly, and a dull glow stick means that the reaction is pretty slow. This glow stick was recently activated. With lots of reactants available to react with each other, it's producing a lot of light. Eventually, one or both of the reactants will be all used up, and no more light will be produced. The light stick will stop glowing.
It's about right. Okay. Why are the two chemical solutions kept separate in a light stick? What happens when they mix? Yeah, they're kept separate because when in contact with each other, um, they with each other they react. They react, and uh, light is produced. Okay. Light stick is made of a thin inner breakable glass tube inside a thicker flexible plastic tube. Contains a solution of one type of chemical and the other outer plastic tube contains a solution of a different one. When the light stick is bent, the inner glass breaks and the solution in the inner and outer tubes mix together. The light given off is the evidence of a chemical reaction happening, yes. Reactants are separate until the user is ready to activate the glow stick. If the chemicals were packaged together at the factory, the reaction would happen immediately and it would be done before the light stick even made it to the store. Okay. All right. So if we wanted to see the temperature of the reactants affect the rate of this light producing reaction, we could heat one stick and cool the other. Let's see what that looks like.
Here we have two identical light sticks. One has been placed in hot water, the other in ice-cold water. They've been in there for a while, so that their temperature should have equilibrated with the temperature of the water in the cup. So one of the glow sticks has hot reactants, and the other has cold reactants. The glow sticks are taken out of the water, and the inner tubes are cracked at the same time. The chemical inside will then contact the chemical that's outside, and the two of them will react with each other. The warm glow stick is brighter, so the chemical reaction must be happening faster. The cool glow stick is not as bright, so the chemical reaction is happening slower. The molecules in the hot glow stick are moving faster. They're colliding with each other more often and with more energy, and so they're producing products more often. This means they'll produce more light and the reaction will happen faster. The reaction will also be over faster. The cold glow stick will actually glow longer but much duller, whereas the hot glow stick will glow very bright but for a shorter amount of time. But eventually, both glow sticks will run out of reactants and no longer form products, and the light will go away.
Mm-hmm. Now, what did you notice when the two light sticks are activated? The hot, the hot water um, glow stick reacted quicker by seeing the light change faster than the colder. Uh, let's see, the colder water glow stick. Okay. How can you tell the reaction is happening faster or slower in each glow stick? By the variation of the brightness of the light produced. Okay. Some people place glow sticks in the freezer to make them last longer. Why do you think this works? Molecules move slower um, in colder temperatures. So to elongate the reaction, you slow the reactants. Okay. Do you think that starting with warmer reactants increases the rate of other chemical reactions? Why? Yes, it speeds up. It speeds up the movement of the molecules. Increased temperature speeds up the movement of the molecules. Yeah, that would make sense. All right. The warm glow stick glows brighter than the cold one. Yeah. They put them in the freezer to make them last longer, so it slows the reaction. Yeah. Uh, the temperature will affect other chemical reactions based on this reaction, because molecules move faster when they're heated. Yeah, so that's good. Um, in the previous lesson, you saw a reaction between sodium bicarbonate solution and a calcium chloride solution in which a gas and a white precipitate were formed. If we wanted to see the temperature of the reactants affects the rate of the reaction, how could we do it? Describe an experiment that would answer this question. Um, I guess I would add hot water. Um, I would add hot water. Uh, uh, Add hot water to hot or hotter water to the reactant side, um, so that it would burn faster to the reactant side, so that in the reaction it would occur quicker. Yeah. See how that works. Place one set in cold and the other one in hot. So one set in cold and the other one in hot, and each set of reactants should be the the same except for the temperature. Pour the two cold together and the two hot together. All right. So the difference would be um, where I put where I said do a hot one on reaction side. So instead of doing a hot side one and a cold side one, and see if there is a difference. All right. So you would make that correction. All right. Reactant heating and cooled sodium bicarbonate and sodium chloride solution. So this is basically the perceived experiment in action. Let's take a look.
In the previous lesson, you saw a reaction between sodium bicarbonate solution, which is baking soda solution, and calcium chloride solution. A gas and a white precipitate were formed. If we wanted to see if the temperature of these reactants affects the rate of this reaction, what could we do? We could place one set of reactants in cold water and one set in hot water so that the reactants start the reaction at different temperatures. Equal amounts of the reactants are poured together. When hot sodium bicarbonate reacts with hot calcium chloride, the reaction is incredibly vigorous. We have lots of bubbles and foam forming. On the left, we have cold sodium carbonate being poured into cold calcium chloride, and the reaction is somewhat underwhelming. You can see the solution becomes a little bit cloudy, but it's nothing like the bubbling, foaming reaction when the reactants are hot. Temperature can play a huge role in the rate of a reaction.
Okay. The temperature of the reactants affect the chemical reaction? Yes. When the reactants were mixed, which one was faster? Hot ones are faster. Why do you think this happens? Because molecules were zooming by. Heated molecules or are sped up and react quicker to each other. Okay. Temperature of the reactants affects how quickly they react, known as the rate of reaction. Yeah, they call it the rate of reaction. And then it gives the understanding of the material thereafter. All right. Now this is molecules colliding and reacting. So this is an animation, so to speak. Let's take a look.
For reactant molecules to react, they need to contact other reactant molecules with enough energy for certain atoms or groups of atoms to come apart and recombine to make the products. When reactants are heated, the average kinetic energy of the molecules increases. This means that more molecules are moving faster and hitting each other with more energy. If more molecules hit each other with enough energy to react, then the rate of reaction increases. When slow-moving molecules hit each other, they'll bounce off without reacting. But faster-moving molecules will hit each other with enough energy to break bonds and react. So again, slow-moving molecules may interact without actually reacting because they don't have enough energy, while faster, more energetic molecules will interact and react and form products.
Okay. In the animation, the molecules moving faster are like the molecules of reactants that were heated in the light stick experiment and the calcium chloride and baking soda solution experiment. In the animation, the molecules moving faster are like the molecules of reactants that were heated in the light stick and the calcium chloride experiments. Yep. The heated molecules move faster as they collide and often harder. The collisions are strong enough to rearrange the atoms to form new products. Okay. The animation moved faster and the molecules are heated. Yep. And the heated move faster as they collide. They're strong enough. Yeah. Cool. All right. So this is basically just explaining what we're looking at. All right. There are many reactants that, when mixed, do not react at all or react extremely slowly at room temperature or below. These reactants need to be heated so the molecules gain enough speed to collect and to collide and react. Sometimes the reaction itself produces enough heat to make more reactants react. This causes the reaction to keep going. All right. All right, let's see what we got. All right, now this is ammonium dichromate volcano. Oh, this is the devil spawn. Okay, I know what you're talking about. It's kind of cool.
This reaction is called an ammonium dichromate volcano. The demonstration shown in this video is very dangerous. Do not attempt to perform this demonstration.
The ammonium dichromate volcano illustrates what happens in a chemical reaction. The orange solid is ammonium dichromate. When a wick soaked in alcohol is placed into the ammonium dichromate and ignited with a match, the higher temperature causes the ammonium dichromate to start reacting. The darker material which is forming is evidence of a chemical change. As the reaction proceeds, it generates heat and the dark solid material is formed more rapidly. Flames and sparks can be seen shooting upward. The orange solid has been transformed into a dark gray-green solid and the temperature has changed. These observations are characteristic of a chemical reaction. A substance with one set of properties is transformed into one or more new substances with a temperature change.
Remember that the reactants were just sitting there until the energy is added with the flame. The added energy was enough to make the molecules move fast and react. The energy produced in the reaction is enough to keep the reactants breaking bonds and making new bonds.
So you heat it up and it goes faster. Wood reacts with the oxygen in there and burns, but a pile of wood sitting next to a fireplace doesn't randomly start burning. You have to start the fire. Why do you think this is the case? Because the wood itself, the wood needs the fire. I'm sorry, the wood needs the fire um, uh, in direct contact, in primarily direct contact, uh, in order for it to start to burn. Contact in order for it to start to burn or ignite. That's the word that they were probably looking for. All right. Molecules woods do react with oxygen, but not at room temperature. So it would have to be there, right? The reactants need to be heated so the molecules gain enough speed to collide and react. When you start a fire, you add energy to begin the reaction. The reaction produces enough heat to make more reactants react. This causes the fire to keep going. Yes, very good. Very cool. And then we got our last one. Let's see. Reactants must be moving fast enough and hit each other hard enough for a chemical reaction to take place. Increasing the temperature increases the average speed of the reactant molecules, and as more molecules move faster, the number of molecules moving fast enough to react increases, which results in faster formation of products. Um, Think of one of the demonstrations that you thought was most memorable. Explain how this demonstration helped you understand the key concept above. Um, well, the second one, right, with the Devil's Volcano, um, it showed that just sitting there, uh, the materials added together at room temperature are non-reactive. But by adding an increased temperature, um, it becomes a volatile reaction, and it goes boom, right? To my one group of students, when we looked at the sodium and the water reactions, you put the sodium on top of the water, and it goes peep 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 peep. Pew, 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 pew. But if you take a big chunk of sodium, you throw it in the water, kaboom! Yeah, it's kind of cool. Yeah. And then the we went through like lithium and sodium and cesium and potassium and magnesium and yeah, all the way down to francium. And then you go down to francium and it'd be like a nuclear bomb going off. So it's kind of cool. All right. How do I feel confident about it? Yeah, I'm good. I still have a couple questions though, and I'll ask about it by email or in class. I will ask about it by email or in class. Email Riccardo. Okay. Riccardo. A copy of your responses will be emailed to aricardo@philasd.org. That's for that one student that was complaining about never seeing my email right here. All right. You hit submit, and then that's it. And then you get your responses. Okay. So hopefully by doing this in the afternoon, I'll knock all the kinks out by the time I'm teaching it in the morning. So see you tomorrow morning. Bye.